Sample exam 4 of 8, problem number 35. Two random samples, each of size 7, are drawn from two independent normal populations, P1 and P2, having the same variance and unknown means mu1 and mu2. Unbiased estimates of the common variance are computed from the samples and denoted as S1 squared and S2 squared, respectively. For what C would the probability of the maximum of these two ratios, greater than C, equal to 0.05? For problem 35, we're going to go over a little background first, and that if S1 is unbiased estimate for sigma squared, it's represented as this. But if you take away the 6 and then divide by this variance that you're trying to estimate, that's a chi-squared with 6 degrees of freedom. And this denominator will play a part in a second. And the same thing for S2 squared. This is the formula, but only the numerator piece is used when finding that it's distributed with a chi-squared with 6 degrees of freedom. So now, to be an F distribution, you need to take a chi-squared divided by the degrees of freedom for the numerator, and the denominator is a chi-squared divided by its degrees of freedom. So in this setting here, so we have S1 squared, you know, when that divided by 6 here is the degrees of freedom, and then divided by the variance. And then so when you invert and multiply, you get this setting here. And then if this is an F, and then reversing those two, they're still both chi-squareds, and it's still a chi-squared, but the numerator and denominator degrees of freedom would flip, but because they're the same, it looks like it's the same. So now when we are trying to find the probability the maximum of those is greater than C, that means that this ratio is greater than C, or this ratio where they're flipped. Well, they're both, this is a F distribution with 6 and 6 degrees of freedom. This is an F with 6 and 6, so this is it. Well, those are the same, so we can rewrite it as 2 times that is equal to 0.05, and that's what it says, but then we divide the 2, so this probability is greater than 0.025, which implies that 6 is 5.8. Problem number 36. Let x1 through xn be a random sample of size n from a distribution with density function f of x equal to 2x over theta squared, where x is between 0 and theta. What is the maximum likelihood estimator of theta? Now, problem 36, we're given this, we find the likelihood function. And the likelihood function means the data are fixed, and we're trying to find the parameter that maximizes this. And note that the range of our x, not the domain, depends upon the theta that we're trying to estimate, which always tends to complicate things, which means that usually an order statistic of some sort is going to play a part in maximizing this. And so if we look at this function, in order this to be maximized, the smaller we make theta, the bigger this overall value is. So we have to make this as small as possible and still be within the constraints. And so since each xi has to be greater between 0 and theta, the smallest that theta can be is the maximum of the data. Well, so that's our maximum likelihood estimate. Number 37. A cookie jar has 3 red marbles and 1 white marble. A shoebox has 1 red marble and 1 white marble. 3 marbles are chosen at random without replacement from the cookie jar and placed into the shoebox. Then 2 marbles are chosen at random and without replacement from the shoebox. What is the probability that both marbles chosen from the shoebox are red? Number 37, let's let T be the number of red on the transfer. And we transfer 3 balls. at a time. So the numbers that it can take on is either 2 or 3. And then after we transfer the balls, we randomly pick 2 balls. And so number of red can either be 0, 1, or 2. We're trying to find the probability that X is 2. Well, if we introduce a variable and then sum over all possible values, it doesn't change. But then this allows us to write it as a conditional density. And then these we know. So when we sum from I equal 2 to 3, we get this piece. And then we get this piece. Well, the probability that we transfer 2 red balls is a hypergeometric. And so it's 3 choose 2 times 1 choose 1 over 4 choose 3. And this one, if we know we transfer 2 red balls, then the probability of obtaining 2 red balls is known. And that's 3 choose 2 times 2 choose 0 over 5 choose 2. It's a hypergeometric. And then the same way when t is equal to 3, we can find those probabilities. And then we simplify and reduce and we get the answer of 3/8. Number 38, suppose x and y have the joint density function f of x is equal to x plus 10 over 3 y squared, where x is greater than 0, y is greater than x, and less than 1. What is the expected value of x times y? So problem 38, we're asked to find the expected value of x times y. So that means that we put in an x and a y times the density, and then we integrate over all possible values. And that's what we do. Let's integrate y first. Y goes from x to 1, and then x goes from 0 to 1. When we multiply that value in, it makes it a little bit easier. And then we integrate with respect to y, so we get 1/2 y squared plus 10 over 12 x y to the 4th. Plug in our limits of integration, and we get this. And now integrate with respect to x, and so this one becomes 1/2 times 1/3 times x to the 3rd. And then you can do that for the same. Plug in the limits of integration, simplify it, you get 31 over 90. Number 39, an automobile manufacturing company produces 3 different car models. The table below presents sales data and average gasoline consumption data for these 3 models. What is the mean miles per gallon for the cars sold by the company, assuming each car uses the same number of gallons of gas? Number 39, this ends up being pretty simple because we use the same amount of gallons in each vehicle. Then though that is averaged out when we take this. So the expected value is each value times the probability of obtaining that vehicle. And the x values take on 15, 20, and 25. And the probability of each vehicle, this was 2,000 over 10,000, which reduces to that. And the same way for these. Simplify, average miles per gallon is 21. Number 40, what is the basic principle of maximum likelihood estimation? On number 40, we sort of addressed this with the question earlier, and the maximum likelihood estimate is you assume that the data are fixed, and then you find the value of the parameter that maximizes it or makes it most likely. And so the answer is A. 41. An urn contains n black balls and n white balls. 3 balls are chosen from the urn at random and without replacement. What is the value of n if the probability is 1/12 that all 3 balls are white? So number 41, we're given that the probability is 1/12 and that we pick all 3 white balls. So that's we choose 0 red and 3 white, and then the total number of ways is 2n over 3, and then this simplifies. This top is, n choose 0 is 1, so we only deal with this, and that simplifies to this. The 3 factorials cancel, and then we have the numerator. And then the denominator, I factor out a 2 right here. And we do that so the n's cancel, and it equals this. Now, if we cross multiply those 2 expressions, it comes down to this, simplifies to this, and n is equal to 5. Number 42. The mean and variance of x are mu, which is not 0, and the variance sigma squared is greater than 0, respectively. If the third moment of x about the mean is minus mu cubed, what is the expected value of x cubed? So here we want to find the third central moment, which is this expression. Well, we want to find the third moment, but we're given that the third central moment is equal to minus mu cubed. So if we multiply this out, we get this, and we're given the variance expression, that the x's are, have a variance of sigma squared. So this comes down, the formula for expected value of x squared is this, and the expected value of x is mu, so that goes in, and this piece and this piece cancel. So then we're here, then if we put in a minus 3 mu here, we get minus 3 mu squared, and we have a plus 3 mu squared, so those cancel, and it leaves just this first piece of here. You take it to the other side, you get 3 mu sigma squared.